Okay, welcome back. We will start the lecture 2 in this unit on thermodynamics, and just to repeat what we just recall what we discussed in the first lecture. I showed you that these are the topics which I intend to cover in first two lecture. We have covered the essential concept and definition, and we talked about heat, energy, work and energy, which will basically continue a little bit more, and internal energy. And in lecture 2 probably I will talk about first law of thermodynamics, calculation of work, heat, different processes, enthalpy and other things which is listed here. In last class we talked about systems, surroundings and boundaries, world. We talked about different systems, open system, closed system, isolated systems, and we talked about different types of boundaries, rigid, non-rigid, movable, impermeable or permeable, adiabatic or non-adiabatic, and we talked about that if you have a movable boundary, then exchange of energy as a work is possible between system and surroundings. If it is permeable, then exchange of materials can take place between system and surroundings. If it is impermeable, then it is a closed system, and if it is a non-adiabatic or diathermal boundary, then energy exchange can possible between system and surroundings as a heat. And you also describe that a system surrounded by rigid, impermeable and adiabatic wall is an isolated system. Then we also discuss how to define the system. State of a system is basically by defining specifying the values of small number of macroscopic variables, which are properties or parameters of system like pressure, temperature and all those things. We discussed intensive properties and extensive properties. I am not going to go in details anymore, and we talked about homogeneous system, heterogeneous systems, phase, processes, which is basically from one state to another state, and we talked about isothermal, isobaric, isochoric processes, cyclic processes. Now, we did not talk about, we talked about that in this unit we will talk about, or in this course we will talk about mainly equilibrium processes or the system which are in equilibrium. Now, what do you mean by equilibrium? Obviously, the first question most of the student answer is that if the values of the properties of the system does not change with time, then we call that system as attained equilibrium. Now, that is a partially true. I will just show you how that is partially true. That definition of equilibrium is applicable or true for an isolated system. So, for an isolated system, if the values of the macroscopic properties do not change with time, then we call that system has reached equilibrium and the values are equilibrium values for the system. Now, for a non-isolated system, two conditions need to be satisfied. One, the macroscopic, obviously the macroscopic properties should not change in time. Secondly, if we remove or if we disconnect the system from surroundings, then there should be no change in the values of the thermodynamic properties of the system. I will just give you a small example, you probably realize. I have a say long rod, iron rod, and one side this is connected to a large pool of water which is kept at say 25 degrees centigrade, and the other side you have a large pool of water which is kept at say 35 degrees centigrade. This is a large pool, okay, and we are just assuming that no heat is exchanged between this rod and the surroundings. Now, what will happen after some time? After enough time, what will be the temperature in this iron rod? This side would be 25 degree and this side would be 35 degree, and there will be a gradient of temperature increasing from 25 to 35 degree centigrade, which will not change with time. If we keep this intact, there will be no change in temperature, obviously pressure, volume are associated with this, there will be no change in the value of those. So, can we call this as equilibrium? No, we cannot call, because if we remove the contact of surroundings, like if you disconnect this part, if you disconnect this part, immediately the temperature will now come back and it will have a average or steady value of 30 degree throughout the rod. So, we need to have for a non isolated system, as I said, that you need to fulfill two conditions: macroscopic properties do not change with time, and removal of system from contact with surroundings causes no change in properties of system. If the first one is fulfilled, in this case point A is fulfilled, then we call the example I gave in just now, we call that as a system is in a steady state, okay, not in equilibrium. So, there is a little difference between steady system is in steady state and in thermodynamic equilibrium. So, you should be clear about what is equilibrium, because we will be dealing only with equilibrium systems in this course. Okay. So, now we will go back the discussion we were having on internal energy. We talked about internal energy, and as I said, internal energy is the energy within the system. So, what are the energies, where from a system get energy within the system is from the molecules which it has, the system has in the system. Now, the molecules can have lot of different types of energy, and especially for gas and liquid we can distinguish them in terms of molecular translational energy, rotational energy, vibrational energy, electronic energy, and we also have the relativistic rest mass energy, which is m rest c square, which is basically the mass. M rest is the mass of the electrons and nucleus which is at rest, but which is not possible to get. That is the reason u cannot be determined, absolute value of u cannot be determined, and this is a constant, this term is constant. So, if you get the difference between u between two states, then this term will cancel out. So, we can get the difference between the values of u in two states. And the another terms we have the potential energy of interaction between the molecules. Now, if we talk about ideal gas, the potential energy between interaction between energy is how much? Because the definition of ideal gas is that it does not have any volume or the molecules do not interact with each other. So, basically this term, the potential energy term, because of the interaction between molecules do not appear. So, value of which is 0 for ideal gas. So, ideal gas, this should be 0, and I am not going in detail about the first 4 terms. This, as I said, this is a constant and this is 0 for ideal gas, and these terms the values are mainly dependent on temperature. They are either constant or dependent on temperature. So, u, if I talk about general system, u would be function of temperature and obviously distance between the molecules, which is governed by either volume or P. And obviously, u is a extensive quantity. So, if you increase the amount of substance, you will also increase. So, you need to give the moles of the component presence in the system, and if you want to get the difference between two states, then is a function of the volume, and if we talk about the closed system, then there will be no change in this number. So, we can just write as a function of temperature and pressure, or temperature and volume. So, what about ideal gas? Ideal gas, because this term is 0 and this is constant. So, del U for ideal gas only depends on temperature, is only function of temperature, or U of ideal gas only function of temperature. Instead of del U, we can write U as a function of temperature for ideal gas. So, if you change the state of, say, if we change the volume of ideal gas without changing temperature, then there is no change in internal energy for ideal gas. If we change pressure of ideal gas without changing temperature, there is no change in the value of U. So, basically if we keep the temperature of ideal gas fixed, obviously in a closed system without changing the amount of substance. If we consider closed system where we are not changing the composition and the amount of substance gas present, then the value of internal energy of an ideal gas only depends on temperature, as if temperature is fixed, there is no change in internal energy. So, just keep in mind that for a closed system, for ideal gas only depends on the temperature, the internal energy, value of internal energy only depends on temperature. Now, we have seen in last lecture that energy can be exchanged between system and surroundings either by doing work or by exchange of heat between system and surroundings. And we also had seen earlier that the total energy change we can equate to change in internal energy for the systems which we normally deals with, where the change in macroscopic kinetic energy and change in macroscopic potential energy is 0. So, total energy change is given by only the change in internal energy. And what are the two ways we can change? We can change by exchange of energy between system and surroundings as heat energy, which we will write as Q, and the other one is by doing work. Okay. So, that we will write as W. So, we can write del U is Q plus W, where Q is the increase in energy due to heat exchange. Q is the increase in energy in the system due to exchange of heat between system and surroundings. Similarly, W is the increase in energy of the system because of the mechanical exchange between system and surroundings. If we have volume constant, volume is fixed. If volume is fixed, then W is 0, because there is, as I said earlier, there is no change in volume, then there will be no energy exchange as work. So, W would be 0. So, in that case we can write delta U would be Q V, where V is Q V means that heat exchange under constant volume. And if we are talking about a adiabatic process, a process which is happening in a system which is surrounded by adiabatic wall, adiabatic process, in this case there is no heat exchange between system and surroundings, which in that case del U would be W, we call adiabatic. Now, if there is no exchange of heat and no exchange of work between a system and surroundings, which happens in an isolated system, an isolated system, as you remember, we described that it is surrounded by rigid wall, which means no change in volume, no work, W is 0, and it is surrounded by a adiabatic wall. So, Q is 0. So, for an isolated system, W is 0, Q is 0, hence del U would be Q plus W, which is also 0. So, this is the mathematical expression of first law of thermodynamics, where it says that for an isolated system, isolated closed system, we are talking about no change in composition or amount of substance. In most cases, we will be dealing with closed system, as I said. So, in case I forget, sometimes you have to remember that in this case the internal energy can be changed by the heat exchange, the work exchange, and also matter exchange. If we add more substance from outside, obviously the internal energy will increase, but obviously we are not considering the case where there is a material exchange between system and surroundings. We are dealing with closed system most cases. So, for a closed system or closed in isolated system, obviously closed system does not matter, it is indeed a closed system. So, there is no matter, exchange of matter is possible. So, for an isolated system, del U is 0. So, that is the mathematical description of first law of thermodynamics. Which says that for an isolated system, there is no change in internal energy, and for any general process, del U is Q plus W. Now, we are talking about closed system in this case. So, one more time, this is a generic expression of first law of thermodynamics, where the change in internal energy is given by Q plus W, where Q is the increase in energy of the system due to heat exchange between system and surroundings across a non-adiabatic wall. Similarly, W is increase in energy of the system due to exchange of energy as work between system and surroundings across a non-rigid wall. Obviously, for an isolated system, both Q and W is 0. So, for an isolated system, del U is 0. Here we do not need to mesh closed system, because isolated systems are indeed, all the isolated system are indeed closed system. So, this is the mathematical expressions of first law of thermodynamics, because thermodynamics first law of thermodynamics is basically obtained for your experimental evidences, which says that energy cannot be created or lost in transformation from one form to another. So, we had seen del U is equal to del W in the systems we are talking about. So, as the energy cannot be created or lost, so in a process del U can be only del U can be changed, or internal energy of the system can be changed by processes which we mentioned now. So, this is what is a mathematical description or of the first law of thermodynamics. So, we will now look at how to calculate work, and just take a simple system where we are taking a cylinder So, this is pressure y axis and x axis we plot volume, and this is the system and this is the initial volume. If we this volume which corresponds to this value V I, which is the initial volume, then we compress we apply a external pressure P x. If it is higher than the inside pressure, then this will move in till the internal pressure is same as external pressure. So, we can have a final volume let us say it has come up to this. So, this is the final volume V f, and the volume change is given by this area. So, this is the area which is the change in the volume. So, that is the initial state where the cylinder has this much volume, which is shown here in this graph, and it has a final volume where it is shown as V f. Now, if the area of this piston is A, then obviously the force given by the piston is given by pressure into area, which is P external into A. The distance moved, it has moved distance, if this is say L, then work done would be force into distance which is given by P x into A into L. Now, this A and L is nothing but the change in volume del V. So, P E x del V or P E x V f minus V I. And if I place this pressure corresponds to P E x, then this area will be equivalent to the work due to this compression. This is the area which is shown in this rectangle. Now, here what happened? The volume of the system has reduced So, the surroundings has done some work on the system, and what happened to the system's energy, increased or decreased. So, in this case system's energy has increased. Now, if something increased, the energy increase means the change in energy has to be a positive number, but in this case V f minus V I del V is a negative number. So, to balance this, we put a negative sign here. So, this negative sign is written or brought in this expression just to balance this. Remember what we talked about in earlier page, that W is the increase in energy. Now, if system is working on the the surroundings is working on the system, which means the energy of the system is increasing, which should reflect in our equation. So, during compression, surroundings work on system, as a result the energy of system goes up. So, the value of W must be a positive number. Now, to make this number positive, we are putting a negative sign in this expression, and it will be fixed all the time. So, there will be no more change in this expression. So, for a compression, when surroundings work on system and system gains some energy, the del V value is negative. So, the W is positive number. So, system gains some energy. If system does work on surroundings during an expansion, if you are doing an expansion where the volume is increased, in that case system is doing work on surroundings, which means system is losing some energy. So, W should be a negative number. So, del V is a positive in that case for expansion, which means W should be negative, which will come negative. So, for compression, del V is negative because V final is less than V initial, and in this compression case surroundings does work on system, as a result the energy of system goes up or increases, which indicates that W should be a positive number because there is an increase. Okay. So, if we write the expression W is equal to minus P E x del V, because del V is a negative. So, this will turn out to be a positive number, okay, for compression. For expansion, del V is positive. So, W is be minus P x del V. So, positive number, negative sign. So, negative number. So, now we are clear that why the negative sign was brought in, and it will be there in all our expression. So, we can write del U as Q plus W, instead of W we can write minus P E x del V, and in this case we are talking about, remember we just talked about one step process where the volume was decreased in one step. That is why the sign P E x, the value of P E x is kept here. Okay. So, this is one step process we mention here, and so this is the expression for your work. Now, if we go back and do the same in multiple step, like if we just do it in pictorially, pressure, and this is the initial volume, and we decreased, we keep the P external here, and as a result the volume get decreased, and then again the pressure is increased, volume gets decreased further, again if I increase, the volume is decreased. So, this is the final volume V f, where we are doing in 3 different steps. First step, we increase the pressure to P 1, which is higher than the internal pressure, and then we change the further increase the pressure P 2, and then we made the pressure P 3, where P 3 is higher than P 2 and P 2 higher than P 1 and P 1 obviously higher than the internal pressure. So, this is the area which represents the work. Now, if I do in infinite number of steps, from this V I to this final volume here, and the pressure, this final pressure is here, then we can have so here we are doing in multiple step. We have in the last page we had shown one step, in this case we are talking about 3 step, and in this case we are talking about infinite number of steps, where we are doing a continuous changes in pressure and volume. Now, just look at, be careful one thing, though I have drawn a line here, ideally there should not be a line, because you do not, when I draw the line in between, that means we are fixing the pressure for these points, which is not true. I have changed the pressure to this value, which corresponds to this. This was my initial stage pressure here, and then I change it here, and then further I change it to here, and then finally I change it. So, I should get only 3 points, and there should not be a continuous line in between, but this has just shown to you just to show that the area which will be corresponds to the work done, or the value of W corresponds to. So, in this case what we know that the area under this curve, the 3 value for W are different when you are doing in 1 step or 2 step or 3 step, which means the value of W depends on, I am going from same volume V f to V 1 and same final pressure, but we are getting 3 different value of the work. So, which means W depends on path which has been adapted for going from state 1 to state 2 or initial state to final state. Now, we know W del U is Q plus W, and U is a state function, because it only depends on pressure, temperature, volume and the amount of substance in the system. So, U is a state function. So, if W is a path function, then q also must be a path function in this case. Okay. Now, in the case this case where we are changing the pressure continuously in infinitesimally small quantity, so that we can draw a continuous line between the initial state and the final state. This process is called a reversible process, and the first two case where we brought the change from state 1 to state 2 in one step or in a discrete 2-3 step, those are called irreversible changes, irreversible processes. In the third example, where we just drawn a continuous line between the initial state and final state, specify all the states in between, equilibrium states in between, that is a reversible process. So, what is a reversible process? Reversible process is a process where system is always infinitesimally close to equilibrium an infinitesimal change in condition can reverse the process to restore both system and to the initial state. So, basically if we changing from one state to another state, if we are changing the volume of a I have a cylinder, if I draw a cylinder here, this is PEX and inside is P. Now, if PEX minus P is infinitesimally small, then the change, if Px is a lower, if Px is infinitesimally lower than P, then this piston will go up infinitesimally small. Now, if you want to increase the volume, a definite amount of volume of this system, then this will take almost infinite time, because the steps which is taking it's in infinitesimally slow steps. So, it is a reversible process are infinitesimally slow process. So, it will take almost infinite time. So, in reality it is not possible. So, it is basically an idealized process. We require the concept of reversible process for several calculations and to derive several thermodynamic parameters. and in this case if the change is infinitesimally small, then if we can go back and write the expression for work done, and if I write the expression for as a dW, which is just talking about very infinitesimally small change in pressure work, then I can write minus Pex dV, where the change in volume is infinitesimally small, and as Px is almost same as P, because they are different than each other, is infinitesimally small, we can write instead of Pex we can write just P. So, this is for reversible process. So, if I want to get the work done for the entire process, I have to integrate from state 1 to state 2 to get the total value for the work done going from state 1 to state in a reversible process, and we knew when we talked about irreversible process. So, this is the value for work done for irreversible process. If I just extend to an ideal gas case, in ideal gas P is equal to nRT by V. So, W would be V1 to V2 nRT by V dV. So, for if I talk about isothermal process, if we restrict discussion for isothermal process, then T is constant, I can take T out of the integral. So, W would be A naught T V 1 by V 2 or initial to final dV by V or A naught to ln V 2 by V 1. So, for isothermal reversible process of an ideal gas, W would be given by minus sign, M is the minus sign here. So, minus LRT V 2 by V 1. Again, for compression, just to recheck, for compression, as V 2 is less than V 1, W would be positive number, and for expansion, as V 2 is greater than V 1, W would be negative number. So, during expansion, system loses energy, and so is actually the energy decreases, and for compression the energy of the system increases. So, W is positive. For free expansion, what is free expansion? When the means Pex is 0, external pressure is 0. So, the expansion is happening in vacuum. So, expansion, when expansion of a gas happens in vacuum. So, P external is 0, then we call it free expansion. So, W would be minus P x del V. So, 0. For if we do it in an isothermal process, now any isothermal process, ideal gas, any isothermal process for an ideal gas, as I discussed in length, del U should be equals to 0. Again isothermal process, ideal gas, del U will be 0. Now, if del U is 0, W is 0, so Q is also 0. So, for free expansion of an ideal gas isothermally will lead Q is equal to 0, W is equal to 0, del U is equal to 0, and for any free expansion all the time, no matter what is the process, isothermal or ideal gas, W would be equals to 0. Now, in this case also, this is also an isothermal process, ideal gas, which means del U would be 0, hence Q would be minus W, which is given by this expression. So, we talked about isothermal reversible process of ideal gas and free expansion. If we talk about adiabatic process, now all the adiabatic process, as soon as you hear the adiabatic process, you will know that Q is 0. The moment the process is adiabatic, which means there is no exchange of heat between system and surroundings. So, Q is 0, which means del U is W adiabatic. And when we talk about isochoric process means del V is 0, which means W is 0, which means del U is Q B. Now, though W and Q are both path function, in these two case, in case of adiabatic process and in case of isochoric process, in adiabatic process W is equals to del U. So, in this case W is no longer a path function. Similarly, in this case Q for the process which happens at constant volume is equals to del U, and del U is a state variable or state function, which means Q in this case does not depend on path. So, Q in this case is a state function. So, remember that not all cases W and Q are path functions. There are cases where W and Q could be a state function as well. So, we talked about adiabatic process, isochoric process. Now, if we do about the isobaric processes like constant pressure process, so del U is Q plus W, I can write Q P because a constant pressure process, and no matter what is, whether it is a reversible process or irreversible process, P can be taken out of integral because it is a fix. Then integral V is V 2 minus V 1. So, in this case no matter, it does not matter whether a process is in reversible process or irreversible process, the value of W would be same P delta V or V 2 minus V 1. Similarly, we in the side also we can write U 2 minus U 1. Now, we can rearrange this to write this is as Q 2 P plus V 2 minus U 1 P V 1. Now, this term U plus V B, we are defining a new thermodynamic parameter H as U plus P V. This is the mathematical definition of H. H is named as enthalpy from Greek word enthalpian, means to work or heat content. Now, you can look at H, you will see that this is only related to U plus P V. All these terms are state variable, which means H is also a state variable. That means, the value of delta H, which only depends on the H 1 and H 2, it does not depend on the path or the process. It has been taken from going to state 1 and state 2. Minus 1. So, it's just I am to say that because H is related to U plus P V, which are who are the terms which are state variables. So, H should be state variable, it should not depend on the path of the system. So, now I can write Q P here as, I can write one more time, Q P we have written U 2 plus P V 2 minus U 1 plus P V 1 as H is equal to U plus P V. We can write Q P is equal to H 2 minus H 1 or del H. So, for constant pressure process, this is the exchange of heat between system and surrounding at constant pressure process, which is the heat absorbed by the system, heat absorbed or increase in energy due to heat exchange, heat absorbed, or simply can write heat absorbed by the system at constant P. For exothermic process, heat gets evolved. So, del H so system loses energy as heat goes out from the system to surroundings. So, del H is negative for endothermic process, where heat is comes in the system from surroundings, in this case del H is positive greater than 0. For most of the cases, like because PV, you can write del H as del U plus del PV. Now, for liquid and solid, this is not a high number, significantly high number. So, for liquid and solids del H value more or less similar to the value of del U, but for gas obviously they are significantly different. For gas we can write, if we take two gases, two condition where we write V A, if we talk about say reaction and product. So, V A is the reactant, N A is the number of moles of reactant. Similarly, V B is the volume of products, N B is volume of a number of moles of. Then we can, if we consider these are ideal gases, then we can write V B is N A R T, P B B is equal to N B R T. Then delta P V is your P B minus P B A R T. So, P B B minus B A gas R T. So, in this case del H del B plus del. So, in a chemical reaction, gaseous chemical reaction, if we assume the gases to be ideal gaseous nature, then we can have this relation between del H and del V, where del N G is the change in the number of moles of gases in the reaction. This is where we are talking about the gaseous reaction, and change in del N G is the change in number of moles of gases. Now, we will just try to discuss little bit of heat. I think time may not permit today. So, what we will do in next class, we will try first thing as to quantify the exchange of heat between system and surroundings as a result of temperature difference, and in that we will bring the concept of heat capacity, and we will take the rest of the discussion from there. So, in next lecture we will start from quantifying or basically setting the equation for heat exchange between system and surroundings.